Hello, in this video we're going to talk about partial pressures. So diving right into it, what are partial pressures? So Dalton's law of partial pressures, named after John Dalton, says that the total pressure of a mixture of gases is just the sum of the pressures that each gas would exert if it was present alone. So let's use air as an example. To a rough approximation, the air we breathe is 80% nitrogen and 20% oxygen. My numbers are off by a few percent, but this will work for now. Okay, so that means if you have a sample of air at 1 atmosphere, you can say that the pressure of oxygen in this mixture is 0.2 atmospheres, because it's 20%. And it would function as if you only had oxygen in there at 0.2 atmospheres and no nitrogen whatsoever. On the flip side, in this sample of air at a total pressure of 1 atmosphere, the partial pressure of nitrogen is 0.8 atmospheres because it's about 80%. And you could represent this by saying PT, or the total pressure, is equal to the partial pressure of one gas plus the partial pressure of another gas. If you have more than 2 components, then you keep going. You add the third gas, the fourth gas, so on and so forth. You sum all the partial pressures, and you get the total pressure. Well, hey, we have mathematical ways to represent sums. So this sigma here is saying the sum over all gases I. If you add all their partial pressures of that gas I, you get the total pressure. Perfect. So partial pressures are important for a couple reasons. One, from the chemical side, if you're collecting gases in a mixture, then you need to know how much of each you have present, but typically you can only measure the total pressure, so you have to know how to kind of subdivide the gases that are inside this mixture. This also has applications for diving, big applications for underwater diving. Maybe a more common one is when you go up in your airplane and the overall pressure drops. If you, say, are breathing air of a total pressure of 0.5 atmospheres, that wouldn't so much be a problem, except now the oxygen partial pressure is 0.1 atmospheres, and that's below the level that our body can handle, and thus you get really sick and die from hypoxia. Okay, another way to talk about partial pressures is this idea of mole fraction, which I'm going to introduce here because it's useful for partial pressures. It's also something that we use in various other places of chemistry as well. So another way we can write this is to say that the partial pressure of some gas is equal to the mole fraction of that gas times the total. So the mole fraction is basically a percentage. You could think of it in the same kind of idea. It's a percentage on a mole basis, and then you divide by 100 to get a decimal form. So that's really all it is. If your sample of gas is 80% nitrogen, the mole fraction of nitrogen is 0.8. Pretty straightforward concept. But remember, we're counting on a mole basis and not a mass basis. Okay, so here's a thorough definition of mole fraction. The ratio of the number of moles of one component to the total moles of all the components present. Again, this sounds just like a percent, except we're not multiplying by 100. So the mole fraction of some component I is equal to the number of moles of that component over the total. Perfect. We use this a lot in chemistry when we're trying to define amounts in a mixture, say, because it's nice to work with mathematically, because when you add them all together it equals 1, and that's a pretty useful number in math. Down on the bottom here, of course, all the mole fractions will add to 1, just like all the percents add to 100. Pretty straightforward. So let's practice this. A gaseous mixture containing some amount of hydrogen and some amount of nitrogen occupies 10 liters total volume at some temperature. What are the partial pressures in atmospheres of both of these gases? Probably the easiest way to do this is to find mole fraction of both gases and work from there. So we need to find the moles of both gases before we can do that. Okay, so we have hydrogen, and we're going to use the molar mass of H2 because the H2 are stuck together covalently as our gas. And so when we're treating them as particles of gas, we need to take into account the total mass of the gas particle, which in this case is H2. So we're using 2 instead of 1 gram per mole. So there's the moles of hydrogen. Then you can do the same thing with nitrogen, again using the molar mass for N2. All right. So the total number of moles in our sample is the sum of hydrogen and nitrogen. That makes sense. Now you could find mole fractions of each right now. In the way I have the example problem formatted, we'll find the mole fractions of each later. Either way is okay. The next thing we need to do is we need to find the total pressure, because our equation here is that the mole fraction times the total pressure equals the partial pressure. So that means we need the total pressure. Well, PV equals nRT, or P equals nRT divided by the volume. And so here's how we would throw this all together. P is the total number of moles for both of them, because we're finding the total pressure that includes both components. R is the ideal gas constant, easy. Temperature, here I converted the temperature to Kelvin, because always convert to Kelvin when it's a gas problem. And then the volume is 10 liters. Double check that all the units in here cancel. We're using the right form of the gas law. That works out. All right, so our pressure overall is 1.99 atmospheres. Now we can find the partial pressures. So the formula here is partial pressure equals mole fraction times total. In this equation, I'm creating the mole fraction in line. So this right here is the mole fraction for hydrogen. And then take the mole fraction and multiply it by the total pressure, and this gives you the partial pressure of just the hydrogen. Then we can do this again for the nitrogen, creating the mole fraction of the nitrogen in line, multiplying by the total pressure, and we get the partial pressure of the nitrogen. Great. So this answers the question. You can always double check that the sum of both partial pressures equals the total pressure, which it should, and here it does. And there you go. That's how you work with mole fraction and partial pressures. Okay, so the big chemistry application of partial pressures that we talk about is what happens when you collect a gas over water. So the situation here is, say you're doing some reaction, potassium chlorate, manganese 4 oxide. So you're doing some reaction here and it generates a gas. This reaction puts out oxygen gas. And if you do this in a sealed system, you can collect the oxygen gas. Well, why would you want to collect the oxygen gas? Well, it's the easiest component out of this reaction product mixture to separate. The oxygen gas will come off, and then everything else will be left over as a lump that's kind of mixed in with starting materials. So if you want to quantify how much of this reaction you run, collecting the oxygen is probably the easiest way to do it. So, well, how do you collect oxygen? So you run this reaction in a sealed system, and this requires some heat. And then the oxygen will travel through this tube, and it will enter a bottle that's initially full of water, like this, right? Here's one that's ready to go beforehand. And then it'll bubble up into here, and then you'll collect the gas in the bottle, and then you can measure the volume of gas that's inside this bottle. For example, say they already made a bunch of this, and here's a bottle that's full. So that seems like a pretty straightforward way to collect gas over water. Water's really easy to use for this. Great. You know, maybe chemically it'd be easier to use mercury instead of water, but it's toxic and big environmental problem and expensive. So water works pretty well for this. Now, the problem is above the surface of the water, there's water vapor that naturally evaporates from the surface of the water. And so in your sample up here, where you're collecting it, you have both water vapor and the oxygen you're collecting, and you need to deal with the partial pressures of both of those. So let me now show you a video to hopefully explain this a little better.
Potassium chlorate, KClO3, decomposes to potassium chloride, KCl, and oxygen gas, O2, when heated. Manganese 4 oxide, MnO2, is added to speed up the reaction. The oxygen gas produced in the reaction can be collected by bubbling it through water and collecting it in a bottle or graduated cylinder. As oxygen gas is generated, the gas bubbles rise to the top and displace water from the cylinder. This method of collecting a gas is based on the assumptions that the gas does not react with water and that it is not appreciably soluble in it. The oxygen gas collected in this manner is not pure because water vapor is also present in the cylinder. The total gas pressure is equal to the sum of the pressures exerted by the oxygen gas and the water vapor. Consequently, we must allow for the pressure of water vapor when we calculate the amount of O2 generated. The partial pressure of O2 equals the total pressure minus the pressure due to water vapor.
Okay. I should define thoroughly what vapor pressure is. This has a large influence in a number of areas of chemistry, and so we should talk about it here. So vapor pressure is the pressure of a vapor in equilibrium with its liquid. And then a vapor is just that substance in the gas phase. So if you have some enclosed system, say this is water, in the air above the water in this closed bottle, there will be water vapor. And there's some amount of it, depends on the temperature of the water. And that vapor consists of water molecules in the gas phase, and then there's a dynamic equilibrium here. So water molecules on the surface are leaving to join the vapor at the same rate as molecules in the vapor are rejoining the liquid. And this comes to an equilibrium state, and so there's a constant amount of water molecules in the vapor phase. Cool. One outcome of this is the definition of a boiling point. So I said, okay, the vapor pressure of water, the partial pressure of water above the liquid inside a sealed system, that vapor pressure increases with temperature. Well, eventually you'll reach a point where that vapor pressure reaches the same pressure as atmospheric pressure above the liquid, and that is called the boiling point. Okay, so now let's cap this off with a big old example. So say you're doing this reaction, you're taking some sodium metal and putting it in water. Well, you're going to make sodium hydroxide and hydrogen gas. And assume for the moment that you don't light the hydrogen gas on fire. Then you collect this hydrogen gas over water. You have some sealed system where you're running this reaction, which, yeah, physically might not be the best idea, but we'll just go with it. Now, if the volume of gas collected is 246 milliliters, and then the overall atmospheric pressure in the room is 0.981 atmospheres, how many grams of sodium did you use in this reaction? Now, when you're doing these problems, you'll need to know what the vapor pressure of water is. And so I give it to you in the problem here. And then you also need to know the ideal gas constant. So here's our plan. So we're going to start with the partial pressure of hydrogen gas, which we need to find, and use that to determine, okay, here's the pressure of hydrogen gas just in this system. Then we can use the ideal gas law to get us to moles of hydrogen gas. And that's the new material. Then it's old stuff that we do stoichiometry to find the moles of sodium, and then use the molar mass of sodium to find grams. All right, let me scoot this up. Let's work with the partial pressure first. So how this works in this situation is, since we're collecting the gas over water, we have the partial pressure of water added into the partial pressure of hydrogen, and then this all equals the total pressure in the room. Your system is sealed, but it's not rigidly held to the same volume. So the volume will adjust so that the pressure inside the system and the pressure in the room are equal. So thus the total pressure is the total pressure of the room. All right, well, we're given in the problem the partial pressure of water, but we got a unit thing to work out. So here's me converting the partial pressure of water into atmospheres by dividing by 760 torr. This leaves atmospheres on the top for this conversion. All right, now let's rearrange this formula. We want to solve for the partial pressure of hydrogen gas. So that's equal to the total minus the water vapor pressure. So then we take the total, we subtract the water vapor pressure in atmospheres, and then this gives us the pressure of just the hydrogen gas in this system. Great. Step one, check. Now, here's the partial pressure of hydrogen gas. Now we can use the ideal gas law to solve for the number of moles. So here it is rearranged for the number of moles. And then now let's plug all this stuff in. This is the partial pressure of hydrogen we're using here. We're not using the total pressure, because if we use the total pressure, it will give us moles of both hydrogen and water vapor, and we don't want that. So we're using the partial pressure of hydrogen here. And then multiply this by the volume. Then you divide by RT. Make sure the units are all the same in here and that they'll all cancel. Great. And then we're going to be left with moles of hydrogen. So now this is the moles of hydrogen produced by this reaction. Then we can move on and do stoichiometry like we always have. Let me pause here for a second to give you a tip. So don't forget to do the partial pressure step first and then put the partial pressure into this PV equals nRT to get moles of just the gas you're looking for. Okay, now we have moles of hydrogen. Let's use the moles of hydrogen to do stoichiometry. So we have moles of hydrogen. Now we want to get to moles of sodium. So our mole ratio is this from the balanced equation up top. 2 moles of sodium react to form 1 mole of hydrogen gas. All right. Now we have moles of sodium. Now let's use the molar mass of sodium to then get grams of sodium. Ta-da! So this many grams of sodium react to produce 246 milliliters of hydrogen gas when collected over water at this temperature and pressure. All right, and that's what we have for this video. Thanks for hanging in there, and I'll catch you later.